So now that we have our project correctly set up, it's time to write our first smart contract. We already have a sample contract here that we don't need, so let's just delete it and create a new file called NFT Market.sol. So usually when people want to build an NFT marketplace, they build or they write two smart contracts. The first one is an NFT contract, and the second one is an NFT market contract. So the NFT contract takes care of everything NFT related, like minting a new NFT, setting token URI to NFTs, getting an NFT owner, etc., etc. So everything that has to do with uh, NFTs, basically. The second contract is the market contract, and this takes care of everything that has to do with buying and selling NFTs. So it takes care of listing an NFT for sale, buying an NFT, transferring ownership upon sale, etc., etc. So two smart contracts. Now for this tutorial, I'm not gonna write two smart contracts because I think we can group all the functionality in just one. Um, So I'm just gonna write one smart contract here. And just keep in mind that if you want to create an NFT collection to drop it in OpenSea or something, you don't have to write the NFT market contract, right? So the NFT market is the OpenSea contract. You only have to write the NFT one and make sure it's compatible with OpenSea, and then you're good to go. So this is not a tutorial on how to do that. We are going to build a mini OpenSea, if you can say so. We are going to need both contracts. It's just that I'm not gonna like write two separate contracts. I'm just gonna group everything inside one simple contract here, and that contract is gonna be named NFT Market. And as you can see in Solidity, we use the keyword contract, followed by the contract name, followed by curly braces. It's kind of similar to classes in object-oriented programming. And one of the similarities is inheritance. So we can inherit or extend another smart contract and get all of its functionality ready for us to use. And that's what we're gonna do here. We're not gonna write all of the NFT logic ourselves because it's already written for us. And we're gonna use the OpenZeppelin ERC721 smart contract, and it's a standard for managing non-fungible tokens or NFTs. Uh, so let's go ahead and Google Open Zeppelin. Actually, we can just go to docs from here, go to contracts, and go to ERC 721. So you can do some reading here, see what this is all about. But basically, the ERC 721 is a standard uh, for uh, for non-fungible tokens, and it's a contract that you can extend from. We have an example here. It's a game item contract that extends from ERC 721 and ERC 721 URI storage. So basically, ERC 721 URI storage here is an extension of ERC 721 that has a little bit more detail. So if you want to read here, it says the ERC 721 URI storage. Is an implementation of ERC 721 that includes the metadata standard extension as well as mechanism for per token metadata, and that's where this set token URI function comes from. That enables us to set different token URIs for each NFT, basically. Another extension of ERC 721 is ERC 721 enumerable. and we can go to the code here and see that it's an implementation of ERC 721 that adds enumerability of all the token IDs in the contract. So this ERC 721 enumerable is good for NFT collections. So if you want to make an NFT collection, um, it's basically NFTs with IDs that go from 1 to, let's say, 10,000, and you want to enumerate those NFTs. So in this implementation, you don't have the set token URI um function because you don't set different token URIs for each NFT, but you like have a base token URI, and then you can use that base token URI and generate all the token URIs from it. Basically, just append the token ID to the base token URI, and you get your dynamically generated token URI. So this is what you want to extend from if you want to build an NFT collection. But for our case, we don't want to do that because we're not going to have the same base token URI for all the NFTs. Um, each NFT we have is gonna have a different token URI, and like we need this token URI to make it work. And by the way, if you don't know what a token URI is, it's basically just the link from where you can get the token metadata. So each token has a metadata, for example, the link to the image of the NFT, the title of the NFT, the description, stuff like that. And you upload that to somewhere basically, and it's generally IPFS, and you get the token URI, and with that URI, you can get the metadata back whenever you want. So it's basically the place where the token metadata is stored. So, in order to use the ERC721 smart contract, we first need to install it. So, if you go back, you see the package that you need to install. Let's go ahead and add it here. Yarn add openzeppelin/contracts. And from here on, we can go ahead and import our contracts. So as I said, we're gonna use the ERC721 URI storage. So let's import it from here. And I forgot to add these two mandatory lines, so the license and the Solidity version. I want to use the latest Solidity version, so I think it's 0.8.11, and let's use that. And while we're at it, let's also update the hardhat config.ts to use the same version. Otherwise, it's going to be an error. And let's go ahead and extend from the ERC721 URI storage. Now, every contract that extends from ERC721 needs a constructor that also calls the parent constructor, as you can see here in the sample code. The constructor for this contract calls the parent constructor, passing in a name and a symbol, basically. So let's go ahead and do that. So constructor, and let's call the parent constructor here ERC721, passing in the name and the symbol, followed by curly braces, of course. And for the name, I can get creative and choose any name you want. I'm just gonna do my NFTs or Abdu's. That's my name, NFTs. And for the symbol, let's do NFT, a NFT. That's as creative as I can get. So it's worth noting that the constructor is a function that takes arguments here, so you can take a string memory, I don't know, address or something, and you can use it here inside the code. What is this? Expected I don't know what's this. Oh, address is a keyword. So you can use AD here. It's basically just another variable. We don't need any parameters, so we're just gonna leave everything empty. So the next thing I'm gonna do is write our first function in the contract, and it's gonna be the create NFT function. So function create NFT. It's gonna be public, and it's gonna take a token URI, which will be a string memory or string call data. Feel free to look these keywords and see the difference between them. So basically, what's gonna happen is that in the front end, we're gonna upload the token metadata and get the token URI of the uploaded stuff and pass it into the create NFT function here. So, and all we need to do in this function is mint a new NFT and set the token URI of the NFT to be equal to this one. So the first thing we need to handle is token IDs. So we want a way to keep track of IDs. I'm gonna go for the simple way here, and in a minute I'm gonna show you a better way. Basically, I'm only going to have a unsigned int 256, call it IDs. It's gonna be private, and we're gonna initialize it to 0. And every time we want to create a new NFT, we just increment this IDs variable and use it in our function. So the first step is to mint a new NFT, and that's done using the mint or save mint function. If you read the docs, it says you need to use save mint as much as like whenever it's possible, because it's safer somehow. And the SafeMint function takes two arguments. The first argument is the address to which we want to mint the NFT to. The second argument is the token ID. So we usually want to mint the token to the person who is calling this function, or to the address that's calling this function. And to do that, we can use the message variable, and it's a global variable that holds information about the current transaction that's being executed. It has a bunch of value of like information like the value, which is how much ETH was sent with the transaction, and it has the sender, which is the address that initiated this transaction. And we are interested in the sender because we want to mint the token to the one who sent the transaction. So that's how we do it. And the second argument is the ID. And here we're going to use the IDs variable. So at first it's going to be 0. We're going to increment it and use it. So the first token will have the ID 1. The second token will have the ID 2, etc., etc. Next, we need to set the token URI for our NFT. And to do that, we call the set token URI, passing in the token ID and the token URI, which comes from the arguments. Oops. And that's it. This is all you need to do in order to create or mint a new NFT to an address. And why not? Let's just go ahead and return the the current NFT ID, and it's going to complain because we need the returns keyword here followed by the type of the variable we're returning, which is an unsigned int 256. Now, regarding token IDs management, as I said, this is the most basic way, but it's not the best. So basically, we don't want to assign random values to our IDs variable, because now we can just do IDs equals 0 or IDs equals 9,000. Like we can assign random values to our IDs variable. Well, we don't want to do that. We want to prevent that from happening. And that's why we should use the counters library. So let's go ahead and import it to see the code here. So it says that this library provides counters that can only be incremented, decremented, or reset. So we cannot assign arbitrary values to the ID's variable. And this can be used, for example, to track the number of elements in a mapping, issuing ERC721 IDs, that's what we want to use it for, or counting request IDs. So counters is the way to go in order to manage token IDs for our ERC721 implementation. So I already imported it, so let's go ahead and delete this variable here and replace it with these two lines. I'm gonna explain what these lines do in a minute, but first let's refactor our code to use the counters variable, the token IDs variable. So in order to increment IDs like this, we do token IDs. Let's just rename this first. So token IDs dot increment. That's how you increment it, and then we can get the current token ID using the current method. So assigned in 256 current ID equals token IDs dot current. So now we have the current ID and we can use it everywhere here. So current ID, and current ID. So this is the more sophisticated way of doing things. And regarding these two lines, let's go ahead and see the code again for this library. As you can see, counters is a library and it has a struct that's called counter. And that's why we do counters.counter. That's the type of the variable. It's basically a struct. And the library also has a bunch of functions, the current, increment, decrement, and reset functions. Uh, but these functions are not inside the struct itself. They're outside of the struct, and even though they're outside of the struct, we can use them with the dot notation here, which is kind of weird. We're not supposed to access a member of a struct if it does not exist in the struct. So in it, for instance, if you do token IDs dot let's do member here, it's gonna complain saying that member not found. Um, yeah, but even though these functions are not in the struct, we are able to use them. And that's because of this line here. So if we comment this line out, you can see that it will complain here. The same error that we had earlier. And without this, the way we can increment the token IDs is to call counters dot increment, passing in the token IDs. So this is how we would do things if not for this line here. So as you can see, this notation is way shorter and way more readable than this one. So let's just remove this and stick with the better one. So I hope this all makes sense, and I guess we're done with the create NFT function, and the next step will be to write tests for it. So let's go ahead and do that in the next video.